Is it those?
I think I'm gonna have access to it.
I have 30 deposit right now.
The fusion card.
If I could see your
Is that engaged?
I mean, you can get it at least at 175. There's the base. There's like that's like standard. Okay, so our test is tomorrow. I think we can get through 7 or all of worksheet 4 by today. So I would like to check your worksheet 4 by the end of class today. Get that out of the way, and I won't have to check. I'll just give you your credit. You won't have to show me any more homework on Wednesday. And then worksheet 5 is optional. I'm not going to be checking worksheet 5, but you can hopefully use that as a final review for you tonight, this afternoon, or wait to go over with me tomorrow morning. I'll do a morning review 7:15 going through worksheet 5. All right. Did we get through number 2 on? So I think I may have rushed a little bit. So let me, so this is page 7. Let me go through number 2 step by step in case some of you are still catching up and we can pick up with number 3. So number 2, we talked about how there's a need for implicits because of the multiple y variables. There's 3 y variables, so we're expecting 3 dy dx's. We're also expecting product rule because it's y times our tangent of y. So those are 2 separate functions. We have to go through product rule. So f prime g plus f g prime. And then we're also remembering our derivative rules that we need to access. Our tangent is u prime over 1 plus u squared. E to the u is e to the u times u prime. Secant is secant tangent. Natural log is u prime over u. So we go through our derivative process. E to the 2y becomes e to the 2y times 2. We're also asking for y's derivative, so dy dx. 2x cubed becomes 6x squared. Oh, sorry, this is I made a mistake and I corrected it, but then didn't do it for this one. Okay, either way, I think I lost that 6x squared, so it should be showing up at the end here. Okay, secant u becomes secant u tangent u times u prime. Natural log of u becomes u prime over u. And now we're just rearranging our terms, collecting our dy dx terms together. So r tangent y, the y1 plus y squared. Actually, all these terms are already together on the same side. Just have to make sure I move that 6x squared over. And then once we factor dy dx out, divide that whole denominator to the other side. Okay, any questions with 2? All right, number 3, we have a related rates problem. All right, fire truck aiming at a window, fire truck X decreasing at 2 meters per second. Is backing up from a building where the ladder is decreasing at 1 meters per second. It lowers the nozzle height, and that's causing that theta to be changing. The stream angle theta must be adjusted. How fast is the nozzle's angle of elevation changing when the truck is 24 meters from the building and the ladder is 10 meters above the ground? So If we create a trig equation that's going to allow us to hit all three sets of information, we're going to use tangent. Now, even though there are x and y values provided, those are a moment in times value, but we can't put that 24 and 10 into the equation. Then we're saying that it's static the entire time through, which is not true. We know that the ladder's lowering, the truck is continuing to back away. So these values are still going to be changing within the triangle. Okay, let's go ahead and find the derivative. So d theta dt will show up. In the right side, we have to go through what? Quotient rule, yeah. F prime g minus fg prime all over g squared. Try that. A lot of these values we have from what's given to us. So let's see if we can identify some of these values. Truck is decreasing. The truck is backing up. So that's decreasing at 2 meters per second. So we can call that dx dt is -2. dy dt, the ladder is lowering as well, -1. A moment when x is 24 and y is 10. So a lot of these values we can plug in, right? We have x, we have y, we have dy dt, we have dx dt, we have x squared. We can put that in. But there's one thing that we still need to look for, and what's that? Get secant of theta, right? Secant squared theta. Make sure that we're trying to find a full replacement for the entire trig function, not just theta. So draw a second triangle. Fill in all the sides of your triangle. Y is 10, x is 24. What can we do to find this missing side? Pythagorean theorem, a squared plus b squared equals c squared. This is ends up being 26. All right, what's secant of theta equal to? Secant. Secant is, yeah, opposite of what? Cosine. So cosine is adjacent over hypotenuse, so therefore secant will be hypotenuse over adjacent. Okay. So yeah, which we can say is 13 over 12. Put that in. Now you're just putting everything in, trying to get that d theta dt by itself. Okay, so try that, see if you can work your way down to your numeric answer. So all this cleans up to be -4/24 squared. I brought that 13/12 over as 12/13 squared. I just entered all this in the calculator. And I just got a decimal version of this answer. Yeah, we can't leave it as in one. You can, if you left it in this form, I'll accept it. Just make sure you include your units of measure. Okay, okay. Yeah. Okay, next page. Number 4, a manufacturing company observes that the cost of producing a certain device follows a pattern where the cost per unit, C of T, is given by C of T, where T represents the time in hours within 24-hour period. What is the average rate of production in the 24-hour period? So average rate, average value, average rate of change, that's slope. So we can just find C of 0, find C of 24, and then just do slope between those 2 points. So average rate of production. So we're just doing C of 24 minus C of 0 over 24 minus 0, just simply slope between 2 endpoints. So find C of 0, find C of 24. Cosine of 0 is 1. 1 times 2 is 2. We get 12 here. Here, 24 pi over 12 is 2 pi. Cosine of 2 pi is still 1. 1 times 2 is 2. We still get 12. So the average rate of production between the 24-hour period is 0. What's the instantaneous rate of production at 9 hours? So now we're looking for the exact rate of change. So we need to find C prime of 9. So let's find the derivative. Ten goes away to 0. What's cosine's derivative? Yeah, so -2 sine of pi over 12t times what? Yeah. U prime is the derivative of the linear. It's just that coefficient, pi over 12. Plug 9 in. See this being reduced to be negative pi over 6. So we know that's going to be in that root 2 over 2, but sine is still positive in the second quadrant. So part C, find the time when the instantaneous rate of change is equal to the average rate of change. So we can just set our derivative equal to our slope. And I meant for that to be in that interval from 0 to 24. So we just set our derivative equal to our rate of change, basically mean value theorem. Just so it's basically this. Okay, so we want to solve this out, work it out through by hand. First off, divide both sides by negative pi over 6. That's going to zero out, which is left with sine of pi over 12t is equal to 0. What can we do next? We're trying to solve for t, so what can we do to work on getting this by itself? Make it what? Pi over 12t equals sine, inverse sine of 0. Right, which is algebraically using inverse trig to help us isolate the variable that we're trying to eventually work towards. Inverse sine of 0 is basically saying the same thing as, okay, what theta value or what t value allows sine of t to be equal to 0. When t is equal to, so sine of what is equal to 0? And theta is, 0, 0 pi. Yeah, I'm just going to keep going. I may not need this many, but I'm trying to solve for t here. So what can we do to get t by itself? Over multiplied by 12 over pi, yeah. So yeah, we're basically having to divide both sides by pi over 12, which is the same thing as multiplying by 12 over pi. And that should clean up that right side for us. So distribute this through. 12 over pi times 0 is still going to be 0. 12 over pi times pi is going to be 12, 24, 36, 48. But the only t-value that we're going to land between 0 and 24 is 12. Yeah, I divide both sides by negative pi over 6, and that's just 0 now. That coefficient just disappeared because I divided. Yeah. And given position, we're just going to find velocity and acceleration. And then find all the places where particles at rest, where velocity is equal to 0. So take derivative. Two pi t becomes just 2 pi. Cosine of u becomes negative sine of u times u prime. Just doing a little bit of cleanup, pushing the non-trig in front.
What are those two cancel?
They wouldn't because this is attached to the sine, so. Okay, acceleration, another derivative down below velocity. 2 pi will go to 0, yeah. And cosine becomes cosine. Two pi t.
Just becoming times 2 pi.
Yeah, times 2 pi.
How?
Because 2 pi t's
Oh, it's
derivative.
2 pi t.
Yeah, 2 pi t, yeah. Okay, what are all the times when particles at rest? Particles at rest is when what? What's equal to 0? Bf equals 0, yeah. Okay, so we're going to move one thing at a time to the right side. Eventually, we're going to get that t by itself. Divide both sides by negative 2 pi. That will get me down to sine of 2 pi t is equal to 1. Isolate that 2 pi t, do inverse sine. Okay, so when is sine equal to 1? When is sine of theta equal to 1? By halves, yeah. Yeah, so just pi halves, but we're gonna have to keep going, adding 2 pi, because we're eventually going to shrink those values down. So I'm going to add 2 pi. So I got 5 pi over 2. I'm just going to go a little further here in case I need them. Okay, one final step, divide by 2 pi. That's the same thing as doing what? One over 2 pi. Pi's canceled out. I'm left with 1 over 4, 1/4, 5/4, 9/4. Okay, we're only looking for values between 0 and 3. I think 13 over 4 is past 3. So okay, let's do a full curve sketch problem. See how far you can get on your own. Find f prime, set f prime equal to 0, create your slope sine line. Find f double prime, set double prime equal to 0. List out your critical points. Neither of the negatives are inside the interval, even though we tried to look for them. So only pi over 6 and 5 pi over 6.
Look back in your f prime, right?
To test your slopes.
And on the test, it'll be oscillating.
Oscillating, yeah. Find an easy test point, 0, into the derivative. 2 sine of 0 is 0, 1 positive.
Wait, why isn't that -1 for sine x?
Oh, I added the 2 sine x over to the right side, left side, sorry, and divided by 2, and that ended up being the same size. Okay, work on F double prime. So when I test 0 into my F double prime, -2 cosine of 0, cosine 0 is 1, 1 times -2 is -2, so negative. And then I can put concave up with it on either side of this. Your relative extremum, you can pull that x value from your slope sine line. Relative minimum is at 5 power 6 because f prime changes from negative to positive. Relative max is at x equals power 6 because x equals power 6 because f prime changes from positive to negative. So practice writing out your because statements. You can also fill out your points of inflection, concave up, concave down, all your because statements simply by looking at your concavity sine line.
Mr. Yang, for the relative extrema, do we need to find a y value?
We will. We'll not right now. We will when we are looking for absolute extrema. We'll plug them back into f prime and find all those order pairs, which we'll need as well for graphing purposes. But for your point of inflection, go ahead and find those y values since, we can do that at this stage. Right here. Yeah, it's the same thing. I just stopped one step short. I already knew that I was looking for x values where cosine 0 is 0, so I just stopped short of it and I just picked out my values without going. But you can go one step further and then write out your x values.
It would be the same thing.
It's the same thing, right? Because I wasn't like trying to divide by 3 or something, so that's why I stopped short of it.
So do you do like the arc sign when
Right, when there's something more than x and I have to go one step further after our trig to divide something out.
Okay.
Yeah.
Do you know the relative min and the max points? I just wanted to see if I got one.
Yeah. Yeah, I didn't find the order pairs for the points of inflection. Let me go ahead and do that.
We need to do that by plugging them in, right?
Yeah, plug it back into the original equation. Let me
The
find
original.
those y values.
It's the original.
Into the original, right?
The original for both points of inflection.
Exactly, yeah. Anytime there's a point involved, you're gonna go back to the original equation.
And put it as an X. Or we put it.
In for, yeah, in for x. So at negative pi over 2, my y value is negative pi over 2. At pi over 2, my y value is pi over 2. For part D, after the extrema, you're finding your highest and lowest points all over the interval. And then this is EBT, you're testing endpoints, critical points, but remember, you're only pulling your candidates from your F prime sign line. Your F double prime sign line is not going to be your potential max and mins. So only these points you have to test. So take all these X values, plug them back into the original function to get those Y values. And then you can also get decimal versions to help you compare between the 4 points, as well as giving you some decimal values so you can know where to plot them on your graph. Okay, so negative pi into the original function, I get negative pi plus cosine of negative pi. Cosine of negative pi is -1, -1 times 2 is -2, so negative pi minus 2 is the y value of my first endpoint. My third point, pi over 6, I got pi over 6 plus root 3. 5 pi over 6, I got 5 pi over 6 minus root 3. And then at pi, I get pi plus -2, which is pi minus 8. Plug them all into the calculator, and I'm just comparing their y values. Highest y value would be my absolute max. Lowest y value would be my absolute min. And then take all of your critical points along with your from your concavity sign line. Get those decimal values plotted onto the graph, and then sketch the graph. It should mimic what we have from our slope sign line. So our slope sign line is giving us increase, decrease, increase, relative max, relative min. And along the way, we're also establishing our concavity. Concave up for the first interval, concave down for the second interval, and then back to concave up. If you have some space on to the right of your graph, let's go ahead and practice our derivative rules. These are the only major three, right? Even though the other three are just negative versions. But also make sure you review your original 6 trig derivative rules. If you have any space next to your graph or any empty space that you have.
Mr. Yang, why are we testing negative pi for the E?
Say it again?
Why are we testing negative pi?
Oh, because EBT says test endpoints and critical points. So endpoints is from negative pi to pi. Because that's, yeah, so endpoints are provided here. And then they're also, basically you're just pulling from your slope sine line. All this you want to test.
But we only tested. Oh, yeah.
And also, they also will help you give you your endpoints that you need for your graphing. Page 14 has all the derivative rules that you need to know. All right, so if I just come around and just check you off page 7 through 9. Okay.
But it's still nice. Yeah, just bring it up. Is yours?
That's all.
So the hospital. This is that.
A lot.
But they don't feel like.
It's like a lot.
Okay.
I can think some of it. Like, it's very.
I mean, I had some big stuff, and so.
I hard to think of it. Yeah. Anyways.
I would have. With like the category. I mean, it is up here. If you just look at the whole way, it goes away, like.
I just gotta think of practices.
No, but you would do.
There's also just like one place.
Anyways.
I'm not focusing.
It's good. No, I can tell you what it's sort of.
I just be tired of something. I got like.
Don't you do one?
Like, huh?
And you do think it's like not a big issue for me.
Yes, but,
Here.
it's like, we were not like, so we were like, I don't think I'm honest, like.
Yeah. Yeah. Yeah.
They look like that's. So I was.
Yeah. Did you get both? Did you get non use?
Yeah. Exactly like Durbin. Okay.
Yeah, if you know the review, you'll be good for the test.
No, I. I was supposed to say for steak and then all my friends were top golf.
Yeah. This could be really bad. It's like when I color. Oh, I mean. You get fifty. It's like. So you can like it's gonna say another something. And sometimes when I take it, it's stuck. Well, like reverse cycle. Was that before? It's like get better. Do you like? That's my dream.
I'll just like find a time to do this tomorrow. I'm gonna bet 8.
Like last Thursday, last Thursday, this Friday, I got signed. Yes, and like, that's it. Like, no,
To make sure.
but it's like, I go to bed at 6:40, but I still. I don't. But it's not like I'm saying something to do that. Yes, like, just like in my bed.
You didn't see this interaction.
It's like, it's all. That's the.
You still like me about it? I used to not be able to do that. 'Cause I used to.
I'll stand.
But now I.